Welcome to another episode of Math 336 Differential Equations, Ordinary Differential Equations. So today we will be talking about section 1.4, and which is on separable equations and applications. So, okay, let's get started. So separable equations are equations that are of this form. They are an equation where the function or the formula that gives us the slope of the solution at the point xy. This is a product of a formula that depends only on x and multiplied by a formula that only depends on y. So we can either think of it as two formulas multiplied together like this, an x formula and a y formula, or we could think of it as an x formula divided by a y formula, right? And actually they're the same. So you can think of h of y is equal to 1 over f of y. So these are really the same. There's no difference between them. So what's nice about separable equations is that, as the name suggests, we can separate the variables. So how does that work? So we separate the variables by taking this f of y and multiplying it up here, and taking this dx and multiplying it up there, and then we just integrate both sides like that. And that's what we get right here. So we end up having the integral of fy dy on the left and the integral of gx dx. So that's called separating the variables. See, all the variables over here are y variables and all the variables over here are x variables. So we've separated the variables from each other. And then that's it. So I'll do some examples where we'll then do this integration, and this will give us the solution to the differential equation. So while we investigate these separable equations and this procedure for solving them, we're going to run across singular solutions. So we're going to discuss singular solutions today. And we're also going to talk about explicit solutions versus implicit solutions. So we'll look at these. So some of these examples will have an explicit solution, and others will only give us an implicit solution. So we'll talk about that. And then finally, we'll do an application of heat transfer at the very end. Okay, so first example today. So this differential equation doesn't appear at first to be separable because it doesn't seem to be of the form that we have above. However, we can rewrite this differential equation by subtracting the 2x y squared from both sides, and we end up getting this 2x minus 2, so dy dx equals minus 2x y squared. And now we see that it is separable, right? So we have, here's a formula that only depends on x, and a formula that only depends on y, and they're being multiplied together. Okay, so that means we can separate these variables. So let's do that. So I'm going to divide both sides by, well, maybe I'll put this just below here, and then I'll write some notes on the side. So we're going to divide both sides by y squared and multiply both sides by dx. So we're going to get dy divided by y squared on the left, and that's equal to minus 2x dx on the right, and then we integrate both sides like that. Okay, so one thing to note, we divided by y squared, which is only allowed for y squared not equal 0, which is the same as that the only time that y is 0 is if, or y squared is 0 if y is 0. So in other words, y is not 0. So that's kind of a restriction that we have in the solution procedure. We're eliminating the possibility of y being 0. So at the end, we're going to have to think about that again. What happens if y is 0? Okay. And this is related to this notion of a singular solution. So we'll see later that this y equals 0 is actually a singular solution of this differential equation. Okay, let's continue for now, and we'll talk about that when it comes up later. So let's do these integrals. So this is the integral of y to the -2. So if I add 1 to that -2, I get -1. And that should be that. Well, yeah, that's it. So if I take the derivative of -y to the -1, then the derivative of this will be y to the -2. Yeah, because this 1 will go down front and cancel this minus here, and then we would subtract 1 from the exponent, and that would give us -2. Yeah, so that is the correct antiderivative. Okay, and then on the right, we're going to have, let's see, this will be -x squared, right? If I take the derivative of that, I'll get -2 times x, yeah. And then I'm going to need to add a constant, which I'm going to call C1. For now, I like my final constant to be C. This is not my final constant, so I'm going to call it C1. And not until the very end will I define what C is exactly. All right, let's solve this equation for y. So let's solve for y. So if we solve this for y, let's see, multiply both sides by -1. So let's do that first. So multiply both sides by -1, get x squared minus c1. Okay. And now that the thing on the left is just 1 over y. So I'm going to invert both sides, and we are going to get y is equal to 1 divided by x squared minus c1. Okay, and now this is basically the final form that I wanted, but now I see the constant there that I would like to replace. So I guess I could leave it this way, that's fine, but I'm going to let c be equal to minus c1, and then after doing that, I'm going to get y of x is equal to 1 over x squared plus c. So that looks nice. I like the way that formula looks right there. Okay. And as we discussed, this is only going to be valid for solutions that are non-zero. So now note y of x equals 0. So just like the zero function, right? If you graph the function, it's just like the x-axis, right? So this constant 0 function is a solution, is also a solution. But is not of the form given here. And by that, I mean, it's not of this form, right? There's no choice for C, which would give us 0 all the time, right? So the only way this would be, yeah, because 1 divided by a number can never be 0, right? So that'll never be 0. Okay, so this this y equals 0, so therefore we call y of x, identically 0, is a singular solution. Okay, so it's a singular solution. All right, so that gives us like kind of a complete solution now of this differential equation. We have this form here. If y is not 0, we have this general form. And then we also have this extra singular solution as well. So that kind of covers all the possible solutions. And why don't we go check GeoGebra and see what the slope field of this looks like. And we'll investigate these two possibilities of the non-singular general solution and then the singular solution, and see if we can find those on GeoGebra. So 1 second here, just gonna pause. Okay, and we're back here in GeoGebra. All right, so let's have a look. So what was this equation that we were looking at? So we want to look at, it was the slope field of minus 2x times y squared. Okay, so there's our slope field. Okay, so you can kind of see what's going on here. All right, so let's try to solve this ODE. See what we get, minus 2x times y squared. Let's see what we get. Okay, so it gave us 1 over x squared, which is definitely one of our solutions. If that c was 0, then we would get the solution, and you can see that matches what's going on with the slope field. And let's just see what happens here. There's a slider here, which will give us different values. Let's just slide it. Oh, there we go. So that's plus c, right? So let's move it all the way over to 5. So 1 over 5 plus x squared. And that gives us, I guess it gives us that solution right there. So let's maybe zoom in a bit. I'm kind of, well, let's reduce this first. And maybe that was a little too much. Let's go to, I want to get 1. Can I get 1? Can I just edit this? I want 1. 1. Okay, perfect. Okay, yeah, that's what we get. But yeah, let's zoom in a bit. That looks weird. What's going on here? 1 second. Let's move this. GeoGebra is struggling here. Okay, 1 second. Okay, we're back. I'm really struggling with this GeoGebra. It keeps freezing up on me. Okay, so I redid it, and here we see the slope field again, and that we solved the ODE in general, and we got this general form here, and we've got this slider, and I don't want to mess with this too much because it seems to freeze up and not doing what I expect. So, but that's fine. So let's just solve this, because I'd like to see some other solutions here. Let's solve this ODE, and we'll ask for like maybe, well, let's give it a point that we wanted to go through. So let's say we wanted to go through the point 0, 4. Okay, and there's the form. So actually this is going to be, if you divide top and bottom by 4, then you're going to get 1 over x squared plus 1/4. So that's the c in this case would be 1/4. And let's try that again. Let's just do another one, solve ODE. I'm a little curious about what's going to happen if I put like a negative initial point. So let's do 0, -1. Okay, so there we go. So what would this be? So I guess what value of c is that? That's actually very strange. So this is actually a different solution entirely. Okay, so that's quite curious. I'll have to think about this a little bit more. I'm not sure. I didn't expect that there would be sort of another family of solutions here. So we'll investigate that a little bit more. But I guess the other thing we wanted to know about is what happens if we go through the origin here, and this should give us the zero solution if it can solve it. Maybe it can't. Oh, I forgot the x. 2x times. All right, not sure if it's going to be able to do this or not. Seems to be stuck. Okay, yeah, when it's undefined, I think it's still thinking, or maybe it's done and it just says like I can't solve this. So that's possible. So GeoGebra is not going to be able to solve every equation automatically. You still have to think about it a bit, but it does provide useful information. All right, so let's go back to the notes and we'll continue the lecture from there. Okay, actually, I see the problem now. So I see the problem. I made the same mistake here. That's why we were getting this strange solution. It almost looks like it's following. Oh, no, it's not. It's definitely not following this slope field. You see the slope is increasing here, but the slope of this curve is decreasing. Yeah, so there's an x missing here. Yeah, let's try that. There we go. That's what we wanted to see. So yeah, I think we do have the general solution. That other thing that we had there was not, that was the wrong ODE that I plugged in there. So yeah, so there you go. So we solved the ODE with the point that goes to the negative, and we got -1 for the constant. Yeah, okay. So now let's go back to the notes. All right, 1 second. Okay, we're back in the notes. So let's look at another example now. Okay, so now what do we have here? So again, this is separable. It's clearly a function of y times a function of x. So let's go ahead and separate the variables. So we're going to divide by y, and we're going to multiply by dx, and then we'll integrate both sides. Okay, so there we've separated the variables. And again, remember, we made an important assumption here. So note, we have to have y is not 0 here. And actually, if you just look at this differential equation, we already see that y equals 0 is a solution, right? If the derivative of y equals 0 is 0, so the left-hand side is 0. So we'll get, if y of x is 0, we get 0 here, and and then on here we'll get 0 as well. So 0 times whatever is 0. So we'll get 0 equals 0, and that's definitely a solution of the differential equation. But in terms of solving it here, so by here I mean in this separation of variables, because we're dividing by y. This is assuming that y is not 0. Okay, so let's go ahead and do this integrals. So the integral of 1 over y is the natural log of the absolute value of y. So don't forget those absolute values. If we actually had an initial point where we know like the y is positive at the initial point, then or the y is negative at the initial point, then we could remove the absolute values, right? So if the initial y point is like y of 0 equals 1, right? 1 is positive, so therefore we know that we're in this area where y is going to be positive. So we can just use log of y. On the other hand, if y of 0 is -1, then we're in this area where y is negative, and then the absolute value of y there is -y. So we would replace this log absolute value of y with log of -y. But because we don't have an initial point, we're just going to keep the absolute values there, And we'll see how we deal with these absolute values as we go through the algebra. Okay, on the other side, we have the integral of sine x is negative cos x. So if we take the derivative of that, we're going to get negative sine, which is sine. Okay, and then plus a constant, which we will call C1. All right. Okay, now how do we solve this for y? So we're going to solve for y. And to solve this equation for y, let's take the exponential of both sides, which I'm going to write using this notation because I'm a computational math person. When you do the exponential on the computer, this is the function. It's exp. So exp of this is going to be the exp of this, right? So just note that exp of x, this means e to the x, right? So that's what that means. So that's what I'm just doing, like e to the power of both sides. Okay, so on the left, the exponential and the log, they cancel, and we're going to be left with absolute value of y. I apologize for my dogs barking. Okay, hopefully that's not too loud. And let's see, on the left, this is going to be like, so this is basically e to the negative cos x plus c1. I think you appreciate why I like exp a little bit better, because it's a bit hard to write everything into the exponent. But we can simplify this right-hand side. We'll get e to the negative cos x times e to the c1, right? So that's the way exponents work. When you have two things with the same base, like e, and you multiply them together, then you add their exponents, right? You add the exponents. So I'm just doing the opposite thing there. I have e to the sum of something. I can split that up into the e of one times the e of the other. Okay, so it's just your standard exponential rule, exponent rule, I guess. Now let's remove the absolute value. So when I remove the absolute value, that will give me, it's going to be a plus or a minus, and I'll move this e to the c1 to the front, and then times e to the negative cosine x. And this is basically the form I want, and now I see what I want my final constant to be. So I'm going to let c equal plus or minus e to the c1, right? And what that means is there's actually a restriction on this c now. So then c is any non-zero constant, right? So it can be positive or negative because of the plus minus, but there's no value of c1 which would give us c equals 0. So it's always going to be a non-zero constant. So that's important to remember. Non-zero constant. Okay, perfect. So therefore, y of x equals c times e to the negative cos x is our solution. And don't forget, we actually also dropped a solution. We dropped the y equals 0 solution. And so in that case, we get a singular solution as well. So what do we say up here? So let's note that y equals 0 is also a solution. Y equals 0 is also a solution, but in this case, we can actually include it into this general form, right? So if I just let C be 0, then I get this singular solution, right? So y of x equals 0, this is a singular solution. So it's a solution. So in other words, it's a singular solution. But which we include with letting C equal 0. So there we have it. In this case, we can actually include the singular solution into the general formula. So now we're going to, this will be our general formula, and any constant C, including 0, is valid and gives us a solution. Okay, well, why don't we check this out? It looks like an interesting differential equation for GeoGebra. So let's head over to GeoGebra and hope it doesn't give us any more headaches. I'll be right back. Okay, and we're back in GeoGebra. Okay, now in this case, what is our differential equation? So it's y times sine x. So let's look at the slope field. Always start with the slope field. Y times, let's see, y times sine of x. Y times sine of x. Okay, nice. Look at that. That is quite the slope field. It's very wavy, as we would expect with a sine function. So that's our slope field. So let's look at some of our solutions. So let's first try to solve this ODE, see if GeoGebra can actually do a good job, do as good a job as we just did in solving it by hand. Let's see what happens. Ah, GeoGebra solved it. Wow, look at that solution. That's pretty cool. All right, let me try hitting play here, see what happens. Okay, cool. So that's what that exponential to the negative cos x looks like for different values. And actually, we might get the C equals 0 here. We should see it completely flatten out when C is 0. Right there, yeah. So it completely flattened out. We got the C equals 0 solution as well. So that is what we expected. That looks great. In this case, GeoGebra is doing a good job for us. All right. Just kind of enjoying watching this. Oh, we can increase the speed. Faster. Awesome. Looks great. So there's all of our solutions of that differential equation. All right, anyway, so let's go back to the notes. Okay, so here we're back. So implicit solutions, right? So in the examples above, in both cases, we were able to obtain an explicit formula for the solution of the differential equation. And what that means is we're always able to solve for y, right? We've solved for y and we got y of x equals something. And those types of solutions are called explicit solutions. And the reason why we make this distinction is because sometimes it is not possible to solve for y. And instead, we're going to get some kind of equation like this, where we have a formula involving x and y, and we're not able to just, solve for y in that formula. It's some kind of formula, and we can't solve for y to get an explicit solution. So in this case, we have the solution of the differential equation, but it's being given to us implicitly. And perhaps you remember hearing this word implicit before. If you remember doing implicit differentiation in your calculus courses, then you remember getting equations like this and then taking the derivative of y with respect to x and then solving for that derivative And that gives you a way to get the derivative of something without being able to solve, have a formula y of x equals something. Okay, so it's not a big deal if we can't solve for y really. But let's look at an example of a differential equation where we just get an implicit solution. So here's the example. So let's have a look at this equation. So again, this is going to be a separable equation. It's not obvious right away, but I guess we could start by just dividing both sides by y. So we'll get x times, y squared plus 1 over y. So let's just make a note over here. Note, I just divided by y, so y is not 0. So let's just keep that in mind. And maybe y equals 0 is a solution. Let me see. Y equals 0, we get 0 on the left, we get x on the right. So maybe it's not a solution. Maybe it's not a solution. So, okay, let's continue. So now we have it in this form, and we can now do our separating the variables. We're going to divide by, I guess I'm going to multiply both sides by the reciprocal of this fraction, and then I'm going to multiply the dx up here. And what do we get? So we'll get y dy over y squared plus 1, and we'll get x dx, and then we'll integrate both sides. Now notice we also just divided by y squared over 1. Oh, sorry, y squared plus 1. So let's think about that. So y squared plus 1. Is it possible for that to be 0? I think no matter what I choose for y squared is always going to be greater or equal 0. And when I add 1, that means it's always greater or equal 1. So actually, here I don't have a problem anymore. I guess I could have just done this in the first place instead of dividing by y at all. So yeah, let me just remove this assumption. This is not a problem anymore. We could have just gone directly from, this equation here. We could just go directly to this without dividing by y. So we could actually just skip this step entirely if you wanted. Yeah, so maybe we should do that. So I could just, let's just forget that we even did that thing. Let's just put a y here, and then we'll put the y squared plus 1, and then all we did was we divided both sides by y squared plus 1, and that's always non-zero. So note, y squared plus 1 is non-zero for all y. So no problem dividing by that, no problem, no restriction. Okay, let's continue. So we want to do the integral on the left and the integral on the right. The integral on the left looks like we want to do u sub. So let's try u sub here. So u equals y squared plus 1, and du is 2y dy. Okay, let's just put that in brackets. And what do we get? We're going to get the integral of the y dy is 1/2 du, so 1/2 du, and on the bottom we get u, and this is x dx. Okay, let's do the integrals. So the integral of this is going to be 1/2 log absolute value of u is equal to 1/2 x squared plus c1. Okay, now let's substitute in. We know u is equal to y squared plus 1. So let's put that in. So 1/2 log absolute value y squared plus 1. Okay, now what about those absolute values? Remember, we were just talking about y squared plus 1. That's always greater or equal to 1. So it's definitely always positive. So absolute value of a positive thing is just that thing itself, right? So we can actually drop these absolute values now. So let's do that. So note y squared plus 1 is greater or equal to 1. So the absolute value of y squared plus 1 is just equal to y squared plus 1. Okay, so nice little note there. And that means that we get 1/2 log y squared plus 1 is equal to 1/2 x squared plus c1. And it looks like I'm running out of space, so let me just add a page. I'll be right back. Okay, added a page. Now we got lots of room to do our calculation here. Let's multiply both sides by 2, I think. I like to get rid of fractions. I hate fractions, so let's get rid of fractions. Do not like fractions. Nobody likes fractions. Okay, let's do the exponential of both sides now to get rid of that logarithm. Nobody likes logarithms either. Okay, using the exponential function. So on the left, the exponential and the log cancel, and we get y squared plus 1 on the left. And then on the right, I'm going to write this as e to the x squared times e to the 2c1. Okay, so just kind of distributing that exponential across the sum, it becomes a product of exponentials, as we talked about. And I think we're almost there. Let's see, y squared is now equal to, let's call this thing here, we'll call that c. So let's just make a note of that. C is equal to e to the 2c1. So that's our definition there. And c is going to be a positive number, always positive. E to the anything, always positive. So c is positive, and we'll get c e to the x squared minus 1. And there we have it. That is that's the best we can do, right? So I can't really solve this uniquely for a y. If I did take the square root of both sides, I would get this plus minus possibility. And we can look at that in a second. But this is our implicit solution. So here's our implicit solution. So here, this is an implicit solution because we're not really able to solve for y uniquely. So in fact, if we were to try to solve for y, what are we going to get? Let's see. Okay, so in fact, both y of x equals the square root of that, and y of x equal negative square root of c e to the x squared minus 1 are explicit solutions. All right, so in this case, we could actually take our implicit solution and we can split it into like 2 explicit solutions. And now if we were to try to satisfy an initial condition, we would have to choose which of these 2 explicit solutions is the one that we should use, right? So if the initial y was positive, we would use the first one, the positive square root. And if the initial y was negative, we would then use the second formula, which has the negative square root. Okay, so let's go to GeoGebra. I'm curious to see what happens when we ask GeoGebra to solve this. So let's head over there right now. Okay, in GeoGebra, let's see what was our equation. Okay, right. Well, I guess in this case, in order to enter this equation in, we actually do have to divide by y. Yeah, so yeah, there's really no way around it. And maybe to make our life a little bit easier here, I'm going to just define this function x comma y is equal to, so f of xy is equal to x times y squared plus 1, and then I'm going to divide all of this by y. Okay, and there is a chipmunk outside who is making that loud noise. Hopefully it's not too loud on the mic. Okay, let's slope field this. Slope field f of x, I guess I just have to say f. Yeah, slope field f. All right, boom, that works. So there's our slope field. Interesting. Interesting. Let's solve this ODE. Let's see what we get. Okay, it found a solution. Does that match one of ours? Yeah, yeah, I don't know why there's a -1 squared. Not sure why they would put a square there, but let's see what happens if we play this. Oh, okay, I see. They're just, okay, that's kind of a weird way to do it. But. So this constant's actually sort of in 3 different places in this equation that GeoGebra is giving us, instead of just in the one place in the formula that we have. But we see that there's that exponential of x squared in there. And I don't see anything on the graph right now for when c is negative. All right, so that's kind of interesting. So there's our solution. I suppose we could solve it as well with an initial condition. So let's have a look at that. So solve this differential equation where the initial condition is, let's see. Well, I'm a little curious about 0, 0, but let's try 0, comma 1 first. Okay. All right. Let's solve it again with a -1, right? And so there you see it, right? This is the positive square root for h of x, this orange solution, and this gray solution has the negative square root. So it's now, depending on the initial condition, it's deciding which of those two solutions is the correct one to use right there. Yeah, and let's just, very curious, what happens when we put in 0, 0, 0, 0. Okay, and it gives us that. Okay, I see. I wonder why it's that one. It could be, see, with 0, 0 is interesting because actually both of them are correct. So actually we would get the top one as well, should be valid, but it's just giving us the one solution. So sometimes you have to be a little bit smarter than the computer in order to understand what's going on here and realize that that's not your only solution that it gave you. It gave us that one, but that's not the only solution. There's another solution there as well. And it would just be the mirror of that. So it would actually look quite cool if we could plot it. So the other solution that it did not give us, yeah, let's plot it. The other solution is square root of the exponential of x squared and then -1. See, that's how it should look, right? It should look like that. There's actually those two solutions. There's the blue solution and the red solution. Those are both solutions, and they both touch right there at the origin. So cool, very cool. All right, let's head back to the notes. Okay, one last thing today. We're going to be looking at this application of cooling and heating, or I guess at the beginning I called it heat transfer, right? So we're looking at the heat transfer equation, and this is a differential equation, and it turns out that this equation is separable, and we're going to be able to solve it using by separating the variables. Okay, so the example is a good example. I mean, this comes up everywhere that there's some sort of a heat transfer going on. But let's think of baking a cake in the oven. So when we're baking a cake in the oven, the heat from the hot air in the oven is being transferred into the cake. So the cake is cooler than the ambient air inside the oven, and that's causing the cake to heat up. I guess it won't get hotter than the ambient air in the oven, so it'll heat up to at most that. But the question is, how fast is it heating up? So what is the rate of change of the temperature? And it turns out that the temperature is going to change according to the difference in temperature between the oven and the cake itself. So initially, when the cake is very cool and you put it in the oven, it's going to increase quite rapidly initially. So the rate of change of the temperature is going to be fast, but then as the cake approaches the temperature of the oven, the temperature is going to gradually slow down. So how do we write this as a differential equation? So let T of T be the temperature of the cake at time T, and A is the ambient temperature inside the oven, and we get that the rate of change is proportional to the difference between the ambient temperature and the temperature of the cake. And it's given by this, where K is some scalar that is taking into account sort of what is this proportionality. So K is another thing that we'll have to determine when we're working on problems about heat transfer. So let's look at an example here. In this case, it's actually an example of removing a cake from the oven and letting it cool down. So we're going to use the same equation for both something heating up and also something cooling down. So we're going to remove the cake from the oven, and when we removed it from the oven, we measured its temperature, and it was 210 Fahrenheit. So the temperature at time 0 is 210. We know that the room temperature is 70 degrees Fahrenheit, and we come back about half an hour later and we measure the temperature of the cake again, and it's 140 degrees Fahrenheit. So at this point, we want to figure out, let's make a timer, and that'll tell us when the cake will be 100 degrees Fahrenheit. We'll set the timer, we'll come back, the cake will be 100 degrees Fahrenheit, right? And maybe at that point, that's when we want to remove the cake from the pan after it's cooled down a bit. So let's go ahead and use differential equations to determine the answer to this question. When will the cake be 100 degrees Fahrenheit? Okay, so solution. All right, so what do we know from the question? So we know the following. The initial temperature is 210. We also know that the temperature after 30 minutes, so we'll measure time in minutes. The temperature after 30 minutes is 140. We know that the ambient temperature is 70, and we want to know when will the temperature be 100. So that's just kind of writing all the information from the problem in mathematical equations. So we want to find the T value for when this thing will be equal to 100. Now, we're going to be using different information here. I guess going back here, I just want to point out quickly that this is our initial condition right here. So right here, that's our initial condition. That will let us solve for this unknown like constant c that will pop up when we're solving the differential equation. This gives us the a. So that tells us what a is in this equation, because this equation actually has, you know, it has two unknowns, right? There's an a and there's a k. So this ambient temperature is given to us, that's a. And what is this information about? Well, that information will tell us what the value of k is, right? So we don't need to know, like look up in a book somewhere, like, you know, under these conditions, what is the value of k? To find out k, come back half an hour later, measure the temperature again. Now we can find out what k is. And that will give us the complete solution to this problem. So that's a good way to think of it. So this will give us the c, this gives us a, and this one will give us our k value. And after we have that, we'll have the solution, and then we'll be able to solve it for this condition, and that will give us our final t. Okay, so let's go ahead and write this stuff down. So dt, d little t is k times the difference in the ambient temperature and the temperature of the cake. Okay, so I promised you that this would be separable. Yes, it is definitely. Oh, I guess I know what A is, right? So let's plug that in first. So A is 70, but I don't know what K is yet. So this is separable. Let's separate the variables. So dt divided by 70 minus t. And let's just make a note over here. For this to be valid, we need 70 minus t is not 0. And indeed, that's going to be valid. So the temperature of the cake will continue to cool down to 70, but it will never actually get to 70 exactly, right? So we're never going to actually have t equals 70. So this is a safe assumption. So we'll plot the solution after, and you'll see that it asymptotically approaches 70, but never actually reaches 70. Mathematically, anyway. Physically, I'm not entirely sure if we could ever say that the cake is precisely 70 degrees. Okay, so there we are, multiplied by d little t, and then integrate both sides. So on the left, we'll have the natural log of 70 minus t, and on the right, we'll have k times t, and we'll have plus c1 right there. Now, what do we know about the 70 minus t? So in fact, in this situation, let's see, maybe I'll just put a note here. Note t is always going to be greater than, or well, it'll, as we just argued, it's never really equal. So t will always be greater than 70. So the absolute value of 70 minus t is going to be what? 70 minus t, that's negative, right? So I would multiply by -1. So that is going to be t minus 70. Yeah, so that's what we'll put in there. So there's a quick note about that. Just scoot that over. So we'll get log of t minus 70 because we're cooling down. If we were warming up, it would be the opposite, right? Warming up, we would get the opposite. But so we'll get this. Exponential of both sides. I'll just exponential both sides like this. Maybe I'll just make this shorter. So I know it's going to be e to the kt, and then there'll be the plus c1, right? But I'm just going to skip that. I don't want to keep doing that same thing all the time. And right there. So I'll just split it up like that. That's what happens when you take the exponential of both sides. So it's okay to skip some steps if you find steps to be tedious and obvious, then it's okay to skip them. You don't have to write every step down. Okay, as long as you're confident that you've got the right answer. Now we get t is equal to 70 plus, and then I'm going to replace this e to the c1 with c. Right there. So c is equal to e to the c1. So c is any positive scalar. Okay, so now we want to figure out what is, so this is t of t. It's always t of t, but maybe I won't write it there just yet. We want to figure out what this k is. And as I mentioned, we can actually do that with this measurement. We set a timer for 30 minutes. We came back after 30 minutes. The temperature was 140. So let's plug that into this equation, and that will let us solve for k. Oh, maybe we should have done, actually we should do the initial condition first. Yeah, because we'll have that capital C in there still. Yeah, let's do the initial condition first. So initial condition was 210, and we plug that in. C E k times 0 is 210. So this guy here, that's 1. So we'll get C is equal to 210 minus 70, and that is 140. All right. So that's our C value. So we got C. Let's just, maybe I'll put it here instead so I can put a nice box around it. C is 140. So we got our C value. Now let's get our K value. So as we mentioned, I hope I got the numbers right. Let me just check. I'm a little bit, because I got 140 there. Yeah, okay. No, I think we're, oh wait. Oh yeah, no, we're fine. Okay, so this is going to be 70 plus, so now we know C is 140. So 140 e to the k times 30, right? T is 30 in this situation, and that is 140. So now we will solve this. Subtract 70 from both sides. Divide by 140. That's 1/2. Logarithm. Don't like logs, but we have to take the logarithm here. So logarithm both sides. We get log of 1/2. Actually, I'm going to write that as log of 2 to the negative 1. And because the reason I wrote it that way is because that will give me negative log 2, right? That's a property of logs. I don't like logs, but I know that if I have an exponent here, I can bring that down front. Okay, so now k is negative log 2 over 30. And that is our value of k right there. Perfect. So, I mean, we could figure out what that is. Maybe let's do that quickly. Just open up Julia on my computer, and I'll do minus log of 2 divided by 30. What is that? So that's going to be like negative 0.0231 and so on. So that's what that value is. So actually in this case, it's interesting. The k here is actually negative, right? Above we talked about when the heat was increasing, we had a positive k, but when the heat is cooling down, we get a negative k. And that makes sense. That makes sense. So we have this. All right, so now let's put everything together. So therefore, T of T is 70 plus 140 e to the, I'm going to change it to exponential. Exponential of negative log 2 over 30 t. I think that's it. Yeah, it's just that. Okay. And we could probably simplify that a little bit. I think there might be a way to have these kind of cancel a little bit. But that's fine. We'll just leave it like that. Just leave it like that. Yeah. Okay, so now let's answer our final question. Final question. When is the temperature 100? When is that going to happen? So just have to solve it one more time here. 70 plus 140 exponential of negative log 2 over 30 t is equal to 100. And we'll get exponential and this stuff is 30 over 140. Take the log of both sides. We're getting close. I can feel it. 3 over 14. And then divide by this log. So we'll get negative. We'll get a log 3 over 14 divided by log 2 and multiplied by 30. And what is that equal to? Negative log of 3 divided by 14 divided by log of 2 times 30. And that is equal to 66.67 and so on. So there's some other numbers there, but that's probably good enough. So that's how many minutes it will take. And I'm hoping that this matches my notes. Let me just quickly check everything here. Yes, exactly. So if you convert that to hours, we'll get after 1 hour, 6 minutes, and about 40 seconds, the cake will be 100 degrees Fahrenheit. And then we're ready to take it out of the pan and put the icing on, I guess. Maybe that's too hot to put the icing on. I don't know. I've never made a cake. But anyway, so that is our application of heat transfer. And it's a great example of a separable equation. So anyway, thanks so much for watching, and I'll see you in the next one. Bye for now.